Hi students, welcome to Year 11 Chemistry and the Introduction to Quantitative Chemistry module. This is video number 9, and in this case we're going to start trying to draw together these ideas of stoichiometry and the mole concept. So very broadly, this video is about how we link moles and mass. We've now done a little bit of calculation around the molar mass for elements and compounds, and looked at the fact that we can express those in terms of molecular formulae or empirical formulae, and when it is most appropriate to do that. Stoichiometry is the application of mathematics. So yes, I'm sorry, but this is now going to be some serious maths applied to chemistry. Well, that's not entirely true. It's not serious maths. In fact, most of the mathematical concepts, as I talked about right at the beginning of this topic, are really around the quantity-quantity ratio idea. And that's what we're going to be doing most often when we deal with moles and converting substances in grams to moles and moles to grams and so on for different types of elements and compounds in chemical reactions. So we're really looking at studying the quantitative aspects of chemistry through our writing of balanced chemical formulae and equations. And when we apply these mathematical principles to these chemical reactions, then we're using stoichiometry. So there's two ways that we can do that here. The first is to look at the number of actual particles. So when we're looking at particles, then we need to make comparisons against Na here, which is Avogadro's number. Now, any of these formulas can very easily be turned into a triangle. As we've looked at before, number of moles is equal to the number of particles divided by the Avogadro number of particles, which is the number of particles per mole. So if we were to look at the electrolysis or the decomposition of water, when we break down water into its two component elements, hydrogen and oxygen, then we have an equation here which represents that process. Two water molecules produce two hydrogen gas molecules and one oxygen gas molecule. And we can see that when we do this experiment because of the 2-to-1 ratio of gases that we produce. If we were looking at it at a molecular level, then we would say every 2 molecules of water produces 2 molecules of hydrogen gas and 1 molecule of oxygen gas. And if we use the mole concept, 2 moles of water produces 2 moles of hydrogen and 1 mole of oxygen. And this obviously makes things much easier for us when we're doing our calculations later on. If we were looking at the comparison of particles, well, then we're going to have to make comparisons around the specific number that relates to Avogadro's number. So if I take this information down, then I'm going to have 2 lots of 6.02 times 10 to the 23 actual molecules of water, and they're going to be producing the same number of actual molecules of hydrogen gas, and this is water, and only half of that, so 6.02 times 10 to the 23 molecules of oxygen gas. So these are just ratios, and this is one of the really important things in chemistry, is that we look at these ratios. Writing and balancing chemical formulae are critical because they allow us to turn each of these expressions into a mathematical calculation that's based on the ratios of each of the substances present. So 2 to 2 to 1 in this case. Now, of course, that's nice, but what we want to do is get this a calculation relating to grams, and that's where we have our little triangle here, which again is in the form of quantity in moles, quantity of mass, and ratio. Formula mass is grams per mole. So we always have a ratio in here somewhere, and then we have 2 quantities. From the previous slide, we said 2 moles of water is going to produce 2 moles of hydrogen gas plus 1 mole of oxygen gas. Now, because we already have started to look at things like the law of conservation of mass, it now means that if we have 2 moles of water, we can actually work out that 1 mole had a molecular mass of 18.016 grams. So 2 moles is going to have twice this amount. And using this value, we can actually work through our formula to work out the exact amount of hydrogen gas, which in this case would be 2 lots of H2, which we also said before was 2.016. So therefore, we're going to have 4.032 grams of hydrogen. And for our last one, all we need to do is look at what the actual amount that's left. And we know that there's only 1 mole of this, so it's 1 lot of 32 grams. So this allows us to make calculations involving moles, mass, and formula mass. And this is something that we'll do a lot of over the next 12 or 18 months. And yes, lots of practice coming. Thanks for watching.